In this final lesson that concludes our chapter on generating data, we will bring together all of the ideas and tools that we learned in the previous lessons. We learned by visualizing histograms that a sample histogram is very different from the histogram of the underlying population. And even if we generate different samples, that each time their histogram will be different from the other. Then we went a step further and we calculated some basic statistics. And we saw that these basic statistics, the mean, the variance, and the median of the sample are notably different from those of the underlying populations. And in this way, the sample statistics will be an approximation of our population statistics. Now we also saw that different samples give rise to different statistics. Each time we generate a different sample, meaning we draw a different number of subset data points from our underlying populations, we will get a very different set of statistics. Now, how do we combine all of these insights that we learned into one final visualization, which also includes some numeric results? Well, to do so, let's go to the code. And in fact, we will finish off the code cell that we started last lesson, where we computed all of the basic statistics for both population and sample. So just to recap, we first computed the population statistics, which we did here, the mean, the variance, and the median. Then we generated a new sample, one for each population. In this case, we took a sample number of 20 data points. Afterwards, we computed the same basic statistics for our samples. And then we put them all into one data frame to compare them. Now, in this lesson, what we will do is we will make visualizations. The first step is to define the figure and the axis in the same way as we did before. In this case, we want a subplot of 2 by 2. So we do plot.subplots with 2 rows and 2 columns. And the figure size is 15 by 10. And these extra parameters here, they indicate that we want to share our x-axis and our y-axis between plots. And then, as the first plot, we visualize the histogram of population 1. And by now, we already are very familiar with how to do this. So we take axis at the position 0, 0, so the top left panel, and we add .hist. We give it as values population 1, we choose 30 bins, and we set the density equal to true. Now the rest of the parameters are basically just layout parameters. The color of the bars, the edge colors, the transparency, and so on. And now we want to visually add the basic statistics that we computed earlier in this cell, the mean, the variance, and the median, on top of this histogram. So how will we do this? Well, for the median and the mean, this is straightforward because they are just singular values. For these, we are going to draw a vertical line at the position of their value. For instance, for the mean, we take this panel, the top left panel, and we add an XV line or a vertical line. Now the position of this V line, this vertical line, will be population 1 mean, the mean of population 1. We give it a color dark blue to really stand out. The line style will be dashed. The line width will be 1.5 and the label will be the mean. But now in this label, we will use the exact value that we computed. And we can do this in the following way. So we can make an F string. So we put F in front of this string. Then we have a string, and between curly brackets, we actually insert the value or the variable that is stored in Python being the value that we calculated. In this case, population 1 mean. And what this does, it includes a numeric value into our plot. And the same thing we can do for our median. We again add a vertical line. The position of this vertical line will be pop1 med, which is the variable for the median that we calculated for population 1. The color will be dark blue, and to distinguish it from the mean vertical line, this time the line style will be dotted instead of dashed. The line width is the same, and this time the label will be an F string with median and the variable pop1 med, which is again the median of population 1 that we calculated before. And in this way, we added both the mean and the median of this population 1, both numerically in the label and visually as these vertical lines. Now, to visually add the variance of our distribution to our plot requires a bit more work, because it's not just a singular value as is the mean or the median. What we're going to do is we're going to shade in an area on top of our histogram, which includes all of the data points that lie within one standard deviation of our mean. Now, in later chapters, we will see in detail why this makes sense to do, and in particular for normal distributions. Now, making this area and shading this in is all done in this line of Python code. And again, I'm not going to go into detail in what it exactly means. If you do want to see this, I gladly refer you to the corresponding video on the YouTube channel Code for Data Science, where I go through these notebooks line by line. Then we set the title Population 1 and we add a legend. And this legend is important because, again, it includes the numeric value of our figures, because in the labels to which this legend looks, we added the actual values that we computed for our basic statistics. And also for our variance of our distribution, we added the rounded standard deviation of our population. And we can do exactly the same for the histogram of population 2. The only difference between this block of code and this block of code is that here we work with population 2. But also remember that in the labels we have to change population 2, because these are the values that we computed for population 2. Now the same can be done for the samples, just to make the comparison. Here we can also do exactly the same. We make the histogram for our sample. We add a vertical line for the mean, which is dashed. We add a vertical line for the median, which is dotted, and we fill in the area that represents this range of data points that fall within one standard deviation of our mean. We add a title sample 1 and a legend, and exactly the same thing we can do for our sample 2. Now all of this code results in the following. If we run this cell, then we see these figures appear. In the top row, we see the histograms of our populations. The top left is our population 1 and the top right population 2. We see very clearly the vertical line representing the mean and the median for our population. In this case, the mean and the median, which we can also see numerically in our legend, is equal to 1. Because remember, we shared our x-axis and our y-axis. That's why on the population histograms, you don't see an x-axis. We also see the shaded area representing the broadness of our histogram. And we see in the legend that one standard deviation is 0.5. Now remember, when generating these populations, these are the exact values that we used to generate them. A mean or location of 1 and a standard deviation or scale of 0.5. Now, population 2 is almost exactly the same, but only the mean is shifted to the right with 0.5. And in the bottom rows, we see the sample histograms, and the same observations still apply. We see that the shape of our sample histograms do not look at all like the shape of our population histograms. And also the basic statistics, which are visually represented by the vertical lines, the shaded area, and numerically visible in these legends, are not equal to their corresponding populations. Now we can see this visually by seeing that the vertical line representing the mean and the median do not align with the vertical line of the corresponding population. Now the nice thing is that we can rerun this cell over and over again, and that we will get a different sample over and over again, and thus a different visualization. So if we do this, we see that each time we get a different histogram and different basic statistics, so different vertical lines. And we see that sometimes the vertical line is to the right of our population vertical line, and sometimes it is to the left of our vertical line of the population. And this just indicates that our sample statistics are very different from sample to sample and also different from our population statistics. Now what we can also see is that whereas the mean and the median were equal for our populations, meaning the two vertical lines overlap perfectly, for our samples, these two lines do not always overlap. In fact, sometimes the median is lower than the average, as is the case in this sample, and sometimes it is larger. So if we just run some new samples and each time generate a new sample, then we see that at this point, the dotted vertical line, which represents the median, is larger than our dashed vertical line, which represents the average. So even these inherent properties, which are present in our populations, the median and the mean being equal to each other, is not always the case in our sample statistics. What we can also learn from this exercise, and which will be very important for the next chapter where we will learn about the central limit theorem, is that each time we generate a new sample, we will get new basic statistics, for instance the average. Each time we rerun this cell, we get a different number. So you can imagine that if we keep generating new samples and we collect the average for each sample and get them all together, they themselves will form a distribution. So we will get a distribution of sample statistics, but more on that in later chapters. What we can still do here, and what I advise you to do for every notebook, is to play around with the figures. For instance, we learned already that if we make the sample size larger, that the approximate statistics will become more in line with our population statistics. In this case, if we keep generating new samples, now with a sample size of 200 instead of 20, we see that our sample statistics, so our lines on our sample histograms, will align more often with the same lines on our histogram of our populations. And this comes back to the fact that the best strategy to get your approximation of your sample statistics more in line with the population statistics is to gather more data. And therefore, we conclude that more data means a better approximation of the basic statistics. Now we can show this in a more impressive way and a more conclusive way by taking our simulation tool to the next level. And that is how we will end this chapter.